Next thing we're going to jump into now, now that we've talked thoroughly about setting up the model, right? So yesterday we talked about setting up the traffic model and all the geometry. Today we talked about some final components with regard to public transit and parking and pedestrian modeling. We're now going to move on to, after the base model is set up, what kind of calibration and behavior types have been used in the model. We already kind of looked at the facility types a little bit, but we didn't really talk about the actual driver behaviors themselves. So that's the first, that's what we're going to jump into now. Um, Now within the Vissim protocol, we do have descriptions of the default driver behavior types. So we have urban motorized, right side rural, freeway, footpath, cycle track. Vissim also has three different types of AV modeling. Pre-calibrated AV driver behaviors. This is less for research level AV, and this is more for just testing penetration rates and things like that. We do have those defaults, although they don't have default link behavior types, but we do have driver behavior profiles if you wanted to include those in the future. But what we need to do next is verify the driver behavior adjustments, if used, are necessary in saturated conditions. So what we're going to be looking at are the driver behaviors and making sure that they make sense for the facility that we are using. Um, Now what we're going to be getting into here with the calibration aspect of it is talking about things like capacity and throughput of different types of movements or facilities. Um, in other types of modeling that you may be familiar with, like intersection capacity analysis or maybe travel demand modeling, all of those elements have capacity, like a facility capacity or link capacity or intersection capacity. Those are all inputs. Those are all starting points for those models, right? So you're going to start with a saturation flow rate with the HCM and then apply adjustment factors, right, to get your final capacity value. In Visum, it kind of works the other way. You're going to start with the behavior of the individual vehicles, their following distances, their speeds, their route choices, things like that, how they interact with each other and infrastructure objects like signals. And then that's going to create an inherent capacity on that facility. And how driver behaviors influence that capacity is by calibrating uh, at the base level, at the most basic oversimplified level is the density component of your flow model, right? So you might think of traffic flow theory as flow equals speed times density, right? The driver behaviors are going to control the density component of that equation. So vehicles that are more aggressive are going to get closer together. The density is going to increase. So for the same speed, you might get a higher capacity, right? And so you can throttle your driver behaviors to create specific throughputs and specific capacities, particularly on uninterrupted flow, freeway elements, things like that. So what we're going to do is start by looking at the driver behaviors, and we're going to see if they've created any customized driver behaviors or if they've changed away from the default parameters at all. And typically this is combined with a calibration um, worksheet, right? So there, or not worksheet, description, right? So here there is a calibration memo that you can go look at and see what processes were involved. This is a requirement as part of the Visum protocols to include a calibration memo. Typically, how driver behaviors are calibrated initially is by going out and collecting field data on things like either max throughput or maybe you're getting jam density values or you're getting headway values. Most commonly, you're going out and getting counts of vehicles, and then you're just taking that. You could take that raw data rather than just the aggregated hourly count or whatever. You could take the raw triggers and just measure the time between each one of those instances and give you, your average headways or headway distribution or something like that. So it's very common to have some sort of headway analysis done particularly on freeways. And then you can go and add that in directly into Vissim or adjust the parameters so that the results output the correct results. So what we're going to do from a reviewer perspective is look at the driver behaviors and see if they've been adjusted away from the defaults, and are they adjusted to realistic or reasonable values. The next driver behavior component beyond just headways that we're going to look at are the lane changes, and making sure that they are sensible, and making sure that the lane change behaviors themselves make sense. One component of that is definitely the driver behavior lane change gap acceptance parameters that we can set up. Another component of that, we already kind of looked at it yesterday, is that lane change distance value. And what we can look at is in the network, we can spot out, we're going to look at some of the speed results in the model. And we're going to look at, are there any points, particularly before an exit ramp or something like that, where there's a lot of sudden congestion, a lot of sudden slowdowns, indicating that maybe vehicles are making last minute speed changes or coming to a complete stop in a lane that they maybe shouldn't be coming to a stop in, which might be indicative of um, lane change behaviors that need to be recalibrated or something like that. Now, just because this behavior is happening doesn't necessarily mean it's wrong. Maybe this is what is actually happening in the field and it's been calibrated to match the field conditions, right? Um, it can be really tempting to calibrate a Vissim model so that it runs perfectly, right? All the flow happens and all the lane changes happen, and it looks like a beautiful model, but it's not representative of real life. So that's the other component, is that we want to make sure that it's representing field data that we've actually collected from the field. All right, so let's take a look at those initial driver behaviors, the lane change behaviors, the following behaviors, and then some of the lane change results. So we're going to jump into our Vissim model, and I'm going to use the drop-down menu. I'm going to find number 27, check behavior calibration. So again, this one looks similar to looking at our facilities again. So we have our link types here um, indicated with different colors. And so in this case, we're looking at the freeway imported and urban imported are the primary ones that were used. And if you remember yesterday when we went through, there were some extra driver behaviors, but we found out that they weren't actually used anywhere. So we're just looking for this 1001 and 1003. So just like we did yesterday, we're going to start by going up to our base data menu and looking at our link behavior types, which are our facility types. So in this case, we have two primary facilities. We have an urban facility indicated in yellow and a freeway facility indicated in this pink color. So I'm going to look for my link behavior types. The reason I want to look first at my link behavior types is because when I select a link behavior type, we can see that it has a name here, and then it also is associated with a driver behavior. So if we use this drop down, we can see, okay, we have a few different driver behaviors. And in this case, the urban one is associated with the urban motorized. The other reason I want to pull this up is because it is not uncommon for a link behavior type to have multiple driver behaviors associated with it. Just as an example, I'm going to open up that Boise model real quick just so I can have something to edit. Um, the other thing you're going to be looking for are things like, for example, there might be a new link behavior type called something like freeway merge, where maybe the default driver behavior is freeway, but maybe the modeler has come through and created some custom driver behaviors where maybe they've calibrated, a freeway merge behavior for cars, and maybe they've calibrated a second one for HGV. Because the way passenger cars merge might be different than the way that your semi trucks merge, right? And the reason we want to look at our link behavior types first is because it is possible in VSIM to have different driver behaviors based on vehicle class. So you might have car and truck, and then they have different behaviors. And so how that will manifest in this list is when you click on the facility type. In this case, you might have a freeway, and if you click on it and there's nothing on the left here, that means that everybody is using this driver behavior that is indicated right here. But if you click on one and it has multiple objects on the left, this is indicating that these two objects are specifically using these driver behaviors and everybody else is using this default one. So that's something that you want to look for initially, is to see, okay, are there any custom facility types or driver behaviors associated by class of vehicles? Um, in this case, if there's no classes over here, everybody's using the same behavior. But again, there might be a differentiation based on vehicle class that you want to look out for. So that's why I wanted to show you the link behavior types first. That's why I always start at the link behavior types first, because I want to check and see if my facility types have any class specific driver behaviors. In this case, I only need to really look at two driver behaviors, because we're only using two facility types and each one only has a single driver behavior associated with it. So I don't really have to worry about this other link behavior type or driver behavior. Even though it's here, I don't really have to worry about reviewing it because it's not used anywhere in the model. So now I can go into base data. Now they know what driver behaviors I'm looking for, I can go into the base data menu and I can look at the driver behavior list. And the driver behaviors, the way I like to think about these is the link behaviors are the facility types, and then the driver behaviors are the behavior profile that drivers use while they are on that facility type. So the driver behaviors are not actually assigned by vehicles. They are assigned by facility, and then when a vehicle drives onto that facility, they adopt that driving behavior, right? And the reason for this is because imagine you're driving to work on your commuter route, right? Every day you drive the same route to work. You're going to have a different driver behavior profile for how you drive through your residential neighborhood and get onto the arterial. You're going to pick up another driver behavior, and then maybe on your on ramp, you're going to be maybe more aggressive because you have to merge into traffic. And then once you're on the freeway, you have a different driver behavior depending on where you are along that freeway, and then subsequently getting off of the freeway again, right? So your driver behaviors aren't homogenous throughout the whole course of your drive. There are times when you become more aggressive, times when you become more passive. And so in this case, we in VSIM also assign driver behaviors by facility type. Um, so now that we know that we're only looking at number 1 and number 3, we don't really have to worry about this other driver behavior, number 41, so I can just kind of more or less ignore this one for now. Now for the urban, the big components that we want to look at for these are the following behaviors. So how are vehicles interacting with vehicles in their own lane? And then the lane change behaviors, how are vehicles interacting while making a lane change? What are their gap acceptances? How aggressive are they going to be, and things like that. So those are the key components that we're going to be looking at there. So what we can do is we can double click on the driver behavior, and the driver behavior settings are differentiated by the behavior type that or by the situation that those drivers are in. So we have the car following model, which has to do with headway and maintaining following distance to the car in front of you. We have lane change. These parameters only are in effect while you as a driver are trying to make a lane change. Lateral has to do with how are vehicles keeping within their lane. Are there any special behaviors that happen around a signal? And then autonomous driving errors. So autonomous driving, fairly straightforward if you're doing any sort of platooning work. And then driving errors, we can implement, typically these are all turned off by default, but you can implement things like lack of attention or over speeding. So if you're doing something like a new ramp with like a clover or something like that, you can actually have distractions happening. You can have misestimation of speed so that cars kind of uh, uh, swerve out of their lane or something like that. So that way you can model some of those more odd behaviors. But that's a little less common. That gets down to um, very facility oriented analysis, trying to analyze different components of design there. The big ones we're going to focus on today, though, are car following models and lane change models. The big ones are the big difference between an urban and a freeway driver behavior are going to be the car following models. So in Vissim, we have different steady state flow conditions um, depending on the speed of the vehicles, right? So in this case, if we're thinking of like a freeway element, um, typically the speeds are a bit higher. It's uninterrupted flow, so there's less start and stop theoretically, unless you have standstill traffic or something like that. Whereas urban streets, you have to interact with conflict areas. You have to interact with signals, potentially jaywalking pedestrians, buses pulling out into traffic, things like that. So they have different car following models because of the nature of the driving behavior that they have. And you guys don't have to commit this necessarily to memory, but the key difference is the urban uses Weidman 74. That is a square root based model. And then Weidman 99 is a more linear model. But basically, what I mean by that is if we are looking at, oops, that's not what I wanted to do. I want to, if we are looking at Weidman 74, let me get my drawing tool out. Okay. If we're looking at Weidman 74, if we have a speed headway relationship, as the speed increases, it kind of looks something like this. If we have our speed versus headway relationship. Whereas if we get into something like Weidman 99, it's going to have a more linear relationship. Um, and the reason for this is because Weidman 74 better estimates headways at really low speeds, speeds less than 30, 25, 35 miles an hour kind of area. And Weidman 99 better estimates speeds at more freeway like speeds, 45 and above kind of stuff. And then there's that middle zone where you can kind of use either one based on the calibration of your model. So, with regard to that, typically what modelers will do is they'll have some version of a Weidman 74 model on their arterials, and then they'll have some version of a freeway of the Weidman 99 model on their freeways and frontage roads and on ramps and things like that. Basically, the rule of thumb that we teach the modelers is, based on the speed of the facility. If your speed is generally going to be pretty high, 45 and above, then you're going to always go with 99. If your speed's always going to be pretty low, then you're going to go with Win 74. Regardless of which model they go with, though, the way you calibrate is going to be more or less the same, in the sense that there's going to be a standstill distance and then a multiplying factor that increases or decreases the headway. So the standstill distance is just that y-intercept. It's just when the speed is 0, how far apart are vehicles, right? And so if we look at Weidman 74 or if we look at Weidman 99, they both have a standstill distance. And so what you can do is you can model the standstill distance based on the jam density of your facility, right? If you have a jam density of um, like 100 vehicles per mile per lane, right? What you can do is you can do a quick calculation, And if you do 5,280 feet per mile divided by 100 vehicles per mile, that means the effective space that each vehicle is occupying is roughly about 52 feet, right? Kind of thing. So if you have 5,280 divided by a jam density of, say, 150 vehicles per mile, that means each vehicle is occupying roughly a space in the lane of about 35 feet. So all you have to do from there is subtract your vehicle length. So let's say your average vehicle length is something like 15 feet. That means that if you have a jam density, a maximum density of 150 vehicles per mile, then your standstill distances are about 20 feet or about a car length, right? And so that's what you'd want to input into this location. So that's typically how they would model something like standstill distances from an analytical perspective. I believe there are guidelines or ranges that you can use in the Vissim protocols as well. Now, with regard to the next factor in both Weidman 99 or Weidman 74, it kind of differentiates a little bit uh, because this is a multiplying factor times the square root of velocity, whereas this one is just a timed headway. So if you're doing a freeway model like this one, basically the headway distribution, you're going to go out into the field, you're going to collect headway data, and then you're just going to create a time distribution. And you can look at your time distribution in the base data menu under distributions and time. The default is zero point 0.9 seconds with no standard deviation. So if I open this up, it's just going to be every vehicle is going exactly 0.9 seconds. But you could always create new time distributions. You could always take these and you can say, okay, I want this to be 1.5 and I want a standard deviation of 0.125 or something like that, in which case it's going to create a bell curve of time distributions centered around 1.5 seconds or 1 second or 2 seconds or something like that. So basically, all you have to do to calibrate the Weidman 99 headways are go out and collect headway data, give you a statistical curve for it, and then recreate that curve in Vissim. And then that will give you that nice headway replication. With the urban, it's a little trickier because it's not a timed headway. It's a factor times the square root of velocity. So this one is more of kind of a trial and error calibration. There are some analytical ways that you can go about calibrating this based on headway data and things like that. Um, but more commonly, what I see modelers doing is just they'll run it with the defaults. They'll see how the assignment comes out and how the results come out. And if the cars are too close or too far apart, they'll make the appropriate adjustments and calibrate accordingly. Um, and so that's more or less what you're kind of looking for with these headway values. Um, is are these within reasonable ranges, right? And for some of these, you don't really need to consider these other ones too much because they're rarely calibrated. In particular, if we're looking at Weidman 99, this looks like a lot of parameters, but the big ones are just going to be CC0 and CC1. So a nice shortcut on looking at these parameters is in the driver behavior list. Just like what we have with the network editor, how we can have different layouts, you can actually have list layouts. So there's a little drop down right here. We can add in a new list layout. I'm going to call this one the default, just so we have what looks like whatever opens when you open up a blank Vissim. And I'm going to hit this little checkbox. So now we have this default list layout. What we could do is we could create other layouts that have commonly used parameters that you're going to be reviewing. Right? So in this case, we might create a new layout by selecting different columns in our list. So I'm just going to remove everything. And what I'm going to do is I'm going to type in W74. And we can see we have our average standstill distance and our additive factor for safety distance. And then I'm going to type in Weidman 99. and we have our standstill distance and our gap time distribution. If I click OK, what this will show is depending on which driver behavior is being used. I think I accidentally switched this to Weedman's. There we go. Depending on which one is being used, it will have those parameters available for you to just visualize. So you don't have to actually open it up and get into it. So here, what we could do is we could add in a new layout. I'm going to call it 01 underscore headway. I can hit the checkbox. And so now I can just at a glance, because you might have 5 or 10 different driver behaviors associated with your model, right? So you don't want to have to double click on each one and then look through all these parameters. You just want to quickly spot check all the parameters and see if they fit within the ranges that are specified. So that's a quick way to do that. The next section that we want to look at are in the driver behaviors are the merging and weaving behaviors. So lane changes with regard to lane drops or maybe acceleration lanes or exit ramps and things like that. So in the lane change behaviors, there's a lot of different driver behavior parameters in here. But the big ones you're looking for are the accepted deceleration of the trailing vehicle, which is the parameter that indicates how much are you willing to cut off the person behind you. And so by making this larger or smaller, that makes the lane changer more aggressive, which improves the number of lane changes out of a lane, but it could hurt the throughput of the through lane because now more people are cutting in front of them and they're getting less speed and things like that. So we have this accepted deceleration, which is often calibrated. We have this safety distance factor. And in VSIM, you're going to see this safety distance in a lot of places. You see it here. You also see it in the conflict area list. You see a safety distance factor as well. All the safety distance is referring to is the minimum headway of a vehicle. So if your minimum headway is 1 second, then that means that you are comfortable following along a car in front of you at a 1 second gap. Well, what the safety distance reduction factor says is while making a lane change, you temporarily become some percentage more aggressive. So in this case, the default is 0.6. So it's saying you are willing to become 40% more aggressive as you make a lane change. So if you normally follow at say 1 second, you're willing to pull in behind somebody at roughly 0.6 seconds, and then once you've completed the lane change, you then recover back to your full safety distance. So again, making this value smaller makes more people more aggressive. And then cooperative lane change is the other big one that we want to look at. This has to do with if you are on the main line and somebody's trying to make a lane change into your lane, do you get out of the way, i.e. do you change lanes to provide a gap for them and kind of get out of the way? That's what the cooperative lane change behavior does. It's not turned on by default, but frequently it's turned on by by modelers. So the big one we want to look at here are these 3 parameters, whether cooperative lane change is on. And then the last one is going to be this wait time before diffusion. Now, we've seen this value before in the error results. If you remember, back when we checked out our error messages before, if I open up my error messages, right, you see this value that says warning, simulation second X, after 60 seconds of waiting for a lane change, this vehicle was removed from a link, right? Well, what that is saying is that a vehicle was trying to make a lane change and they hit this upper limit of waiting. And so what VSIM did was assume that that was a one-off error and would delete the vehicle to hopefully keep traffic moving. So the vehicle just gets deleted from all data, basically, and then logged in the error file. If this wait time before diffusion is really low, around 60 seconds, you're going to have more of those vehicles getting deleted, especially if you think about something like signals being, 90 to 120 seconds, and there's a car waiting to make a lane change, but the signal is red. If that car has to wait for more than 60 seconds, they're going to be deleted. And so if you have a lot of those errors popping up, it might be worth considering increasing this wait time before diffusion to see if that's more a function of the facility or is that a driver behavior calibration issue. So this is a good indicator for something like that. So just like we did with the headway behaviors, what we're going to do is we're going to create a new layout for our list, and we're going to look for the lane change behaviors. So in this case, we're going to do accepted deceleration of the trailing vehicle. We also looked at that wait time before diffusion. Diffusion, I think it's called diffusion time. We are going to do the safety distance reduction factor for lane changes. And we are going to do cooperative lane change with the maximum collision time and maximum speed difference. And so what we could do is we can save this as 02 underscore lane change. Check that box. So now we have the default parameter set, we have the headway parameter set, and we have the key parameters for lane changes, right? And so all you have to do now is go through and double check and see, okay, have things been adjusted or calibrated or something like that. So we can see on the urban, cooperative lane change is turned off. On the freeway, cooperative lane change is turned on, and the accepted deceleration is different for each driver behavior. So these are quick ways that you can go through and calibrate these parameters. Or not calibrate, review these parameters, sorry. Okay. Once we've looked at the driver behavior parameters and we've checked that they're all within acceptable ranges and they make sense with the context of the particular model that you're looking at. The other thing we want to do is use our drop down and look at the lane change locations. Sorry, this is taking a second to load. Just give me 1 second. There we go. What this is doing is this is actually displaying the simulation data right now. So when we ran the simulation, one of the evaluations we collected was called link evaluation. And as a result of that link evaluation, what it does is it collects speed on different sections of the network. And so what we've done is we've taken our links and we are displaying our links colors based on that reported minimum speed that was reported. The reason we're checking the minimum speed is because we want to spot out those areas where vehicles may have been stopped or slowed down for whatever reason. And these are in 15-minute intervals. So this is over the course of a 15-minute interval, what was the lowest reported speed of any of the 15-minute intervals is what we're looking for. And so what we have from a label perspective is we are also looking again at that lane change distance. So what we can do is we can move around, and what you want to do is you just want to spot check, in particular things like freeway exits and freeway on-ramps and lane drops, and see where speeds are low. So for example, here's an off-ramp where roughly the cars are going, around 45 miles per hour. Whereas the main line is more than 50. And you see temporarily for this lane, they drop to 45. But that makes sense because there's not much of an exit lane, so vehicles have to make a lot of last minute lane changes. What you might look for is, for example, on the other end, if we look at this lane, well, the main line is all, the minimum speed is above 50 miles per hour. But if we look at this acceleration lane, there was some point in the simulation where cars were going for an entire 15-minute period, or for on average over the course of a 15-minute period, they were going 25 miles per hour. But the main line was not. So that's telling you that maybe there was a section, this section that they were having trouble merging or something like that. Because you see this very large discrepancy between the minimum speed on the acceleration lane and the minimum speed on the freeway link, right? So there might have been a bunch of vehicles stuck at this location. You might also want to, at this point, note the link number that we are at. So this is, if I hover over it, you can see it says link number 232. And it might be worth coming into, not the Boise model, sorry, I want to look at our sample file error results, right? You might look at an error result and see if link 232 comes up as any one of these links where cars are getting deleted, because that would indicate that vehicles are having a hard time merging or something like that. So you could always go through it and look for a link type of 232, right? So I can, I do link 232 and hit find next. Okay, so cannot find. Let's look up real quick just to double check. Okay, so it doesn't look like there were any errors that popped up on this particular link. So that's okay. That means that all the vehicles were able to at least merge at some point. They weren't getting deleted because they were unable to merge. I'm looking at other locations. Like for example, here's a difference where they were accelerating up to freeway speeds, but more or less these speeds are fairly close together. So that's a good merge location. What you're looking for is any locations like this one where vehicles are suddenly stopping, right? So in this case, if we quickly switch over to the default view just to see what the lane configuration is, right? They have a long run-up time, a long exit lane run-up time with 2 lanes exiting. But for some reason, there's a bunch of vehicles making a last-minute lane change within the last, couple hundred feet. So 250 feet, even though the lane change distance is 3,500 feet, there are vehicles that are, for some reason, driving all the way up to the very end point and getting over. Now, that could be because the right lane was jammed up or something like that, or the density was just high enough that they weren't able to find a good enough gap. And so what happens is as they approach the exit, they start slowing down because they're about to miss their exit. And so sometimes what happens is they slow down and then dive in at the last second. So this might be an issue with lane change calibration. It could be an issue with the lane change distance. So that might require some further investigation there. So that's the kind of stuff you're looking for with those lane changes. It can be a little bit trickier to do this same analysis from just this view on the arterials because there's so many signals and other things going on that it's hard to tell if these stop conditions are because of the signal head or if it's because of bad lane change behavior. So that will require further investigation with an animation review where you go back and you look at how the simulation is running, and we'll do that in a little bit.